In this video, we're going to discuss enthalpy. As an example of a couple of reactions that we can define as the system, in this case we have a reaction in which the ammonium nitrate is dissolved in water, and we know that this is an endothermic process when we go from the solid ammonium nitrate to the ammonium ions and nitrate ions in solution. The heat will go out of the liquid water and into the products of this particular reaction. And if the question is what is the sign of Q, all right, the sign of Q must be positive, and the reaction vessel will appear to get colder. If we have another example, in this particular case, we have the reaction between elemental hydrogen and elemental oxygen in the gas phase, producing water molecules. In this case, this is an exothermic process. We have a situation where the reactants have a fair amount of stored potential chemical energy in the bonds, and that energy is released when we go to the products because the bonds between the oxygens and the hydrogens in the product water molecules are not as don't have as much potential chemical energy. And so the question is, what is the sign of Q in this case? And Q must be negative. And will the reaction vessel feel warm or hot? Okay, since the energy is coming out of this chemical reaction, it's a product. It goes into the surroundings, and so it will appear warmer. And finally, we have three terms that we need to deal with. The first is the concept of an extensive property. Extensive properties depend upon the amount of substance that you have, whereas intensive properties are independent of the amount of substance that you have. And then finally, we have the concept of a state function. A state function is something that is independent of the path that you take to get there. So a really good example of this on the macroscopic level is climbing a mountain. So if we were to climb from the base of the mountain to the top of the mountain, we would gain some gravitational potential energy as a result of doing that. Likewise, if we were to take a very windy path to get to the top of the mountain, we would still end up having the same amount of gravitational potential energy once we got to the top of the mountain as we did by climbing straight up. Chemical reactions are like this as well, and so we can store energy in chemical bonds, and it really doesn't matter how we get to that particular species in terms of the route that one would, synthetic route that one would take. At this point, we want to discuss the relationship between internal energy and enthalpy. Turns out that the change in heat for a particular reaction, if we have a constant pressure, is known as the enthalpy of the reaction. And so the enthalpy of a reaction is an extensive property. It depends upon the amount of material used in the reaction, and it is also a state function because it doesn't matter the path that you take to do that reaction. So we can write these relationships. So the change in internal energy is equal to the heat at a constant volume. The problem with this is that that changes the pressure of the system if the volume can't change. Alternatively, the change in enthalpy is equal to the amount of heat involved if we have a constant pressure, and therefore the volume can not be a factor in this. This really comes down to why these two things are different is because if we have a situation where the volume can change, then that can do work, and that energy into a different direction. As an example of this, if we consider the reaction of hydrogen, elemental hydrogen with elemental oxygen in an open vessel, the products are going to be gaseous water. Since the pressure is not going to be changing, the amount of heat that is produced by this reaction will be the enthalpy of the reaction. So in this particular case, if we do this reaction, we would produce approximately 572 kilojoules of heat when 2 moles of hydrogen react with 1 mole of oxygen. And so in this particular case, then our heat is negative because this is an exothermic reaction. The heat comes out of the reaction and goes into the surroundings. So delta H is our negative 572 kilojoules. So as a result, then we can talk about the energy associated with the reactants, which must be higher than the energy of the products. The products are more stable, and this produces 2 moles of water as a result of doing this reaction, along with the 572 kilojoules of energy. At this point, we can more precisely define the relationship of enthalpy, entropy, and work. And so it turns out that the enthalpy of a reaction is equal to the internal energy plus the pressure times volume. And of course, this is what we would be measuring. So delta H, putting the symbol of delta in front of the H, is telling us that we're talking about a change in the enthalpy, and delta is always final minus initial. So to determine the delta H of this reaction, we need to talk about the internal energy of the system plus the pressure times volume of the final situation minus the internal and pressure times volume for the initial situation. And of course, then we can simplify this by rearranging the equation, and we come up with the overall relationship that delta H is equal to the change in delta E plus the P delta V. And so in this particular situation, if P is held constant, the volume can change. And as a result, the final conclusion is that the change in E is equal to the change in H minus the pressure times the change in volume. And the crucial thing here is this pressure times the change in volume is going to be able to do some sort of work. So if we focus in on this equation, and in particular the P delta V, the only way that the pressure could remain constant is if the volume changes. And of course, then if the volume changes, we're able to do some sort of work as a result of that. And so we define work in this case as the negative P delta V term in this equation. To help you visualize this, perhaps, we can consider the reaction of an active metal such as sodium with water, which is going to produce the gas hydrogen, H2 plus some sodium hydroxide, and along with some heat. If we do this reaction in a very special container that has a piston associated with it, where the piston can move up and down, and as a result, if there is any kind of production of the gas, which would cause a pressure change if the volume couldn't change, then as a result the piston might rise, and as a result then we would then maintain a constant pressure. So by producing the gas and doing the reaction, we're going to do some sort of work which increases the overall volume that the system is contained in, that maintains the constant pressure, but we've done the work of pushing the piston up against the force of gravity.